Okay, so we left off with a kind of exploratory exercise, which was thinking about Laplace functions mapping as mappings from the complex plane to the complex plane. And the net result of our exploration was kind of this statement up top, is that if in the domain the contour encircles p poles and z zeros of the function, you should expect p minus z counterclockwise encirclements of the origin in the range space, in the resultant of that contour. So this equation, n equals p minus z, is very easy to write, but you have to decode it quite a bit to get at the insight. And it's complicated by the fact when you Google Cauchy's argument principle, about 3/4 of the results will define n in the reverse way, as the number of clockwise encirclements. I only noticed that once I wrote this slide. But just as a heads up, if you find this on a website and it says n equals z minus p, that's because that n is counting clockwise encirclements. So it works the same, it's just a negative. All right? But what I'm going to go forward is the notation that one pole and no zeros encircled results in one counterclockwise encirclement. So if, for example, we have this contour, and we'll go clockwise around that contour, I think we are encircling, so this would be t equals 2, z equals 1, and so we should expect one counterclockwise encirclement in the resultant, in the range space. Okay. This pole, because it's not in the contour, doesn't come into practice, doesn't come into play. And yeah, so I think I did plot this beforehand, and you get something that looks like, here, let me make this easier on myself. So this is a combo. On Monday, all of the domain plots were over here and the range plots were over there. This is squashed onto one set of axes, where white is domain contour and yellow is range contour. So tell me, based on this algebra, what direction should I draw this arrow? Should it be that way, or should it be that way? This says one counterclockwise, and so I think we're facing this one. Good. Good.
Oh, because it's the counterclockwise around the origin.
Yeah. Because there's lots of loops, I'm only counting the orientation of the encirclement of the origin. Yeah.
Also, the pole just doesn't come into play about the number, or that pole outside of the contour doesn't come into play about the number of encirclements. It does come into play for like that.
Yes, if I remove this, then I think I'll probably lose that squiggly bit there. Okay. But I won't change the number of encirclements.
If n was 2, it would move the other way.
If n was -1, it would be the other way. Yeah. If n were 2, it would have this and then another go. Yeah.
How does this apply to counterclockwise contours?
Everything would be reversed.
Okay.
Yeah. So if you learn it one way, everything just gets reversed the other way. Okay, so again, this n equals p minus z is attributed to Cauchy, and it, for a while I wondered, like, what a weird collection of ways to, but argument in the sense of like input to a function. That's the argument in the argument principle. We can also apply this in the other direction. So we had n equals p minus z. If we know two of these things, we can get the other. So in particular, we are mostly going to use it in this way. if I know the number of poles that a contour encircles, and I know the number of resultant encirclements of the origin, then I can work out how many zeros the domain contour encircles. Okay. So this is most applicable when our domain contour looks like the following. So here's the imaginary part of S. So this is a purely domain plot. And then this would be our range plot. Real plot, what do I call it? Some F. So let's say that we know that there are, well, okay. What region of the S-plane would be really nice to know if there were any poles or zeros in it?
Right.
Yeah, I mean, I want to know where the poles are and the zeros are over here, but their locations. But in terms of aggregate number, it would be really nice to know how many were kind of vaguely in the entire right half plane. So that is why this is a contour of interest to us. In fact, it gets its own name. This is the contour that, if you like, starts at the origin, goes all the way up the imaginary axis, on the imaginary axis, until it gets to infinity radians per second times j, and then it comes all the way around. I've drawn it finite because I don't have long enough arms to get to infinity. Then it comes all the way around to negative j infinity, and then back up to the origin again. Okay? In fact, this is called the Nyquist contour.
Does it have a specified field crossing, or it's just somewhere
At infinity.
at infinity?
Yeah. Mark?
Does it encircle the origin?
It goes straight through the origin.
So how,
We'll worry about what happens if there are poles and zeros on the imaginary axis in a moment. But for now, let's just say this contour, if there are poles and zeros in the right half plane, this will, strictly in the right half plane, this will encircle us. Is everyone all right with that? If you're not comfortable with this going to infinity, perhaps you can think about, well, if there are any poles and zeros, they'll be at finite locations. So all I have to do is pick a radius bigger than the biggest of those radii and go around them. Okay, so if we know that there are no poles of this f function inside this contour, i.e. strictly in the right half plane, and we know that the resultant looks something like this, how many zeros can we conclude lie in the right half plane? Let me switch this around. Oh, wait, this was, oh, sorry, this is better. This is clockwise encirclement. 1, 0. Okay, so what I was trying to get you to see is that if we treat this as z equals p minus n, and we are told that there are no poles in the right half plane, and we can observe that there is -1 counterclockwise encirclements of the origin, then we have to conclude that there is a 0 somewhere in here. Okay? That is how, believe it or not, we're going to use this result. Okay, so that's how it's going to apply to controls.
Don't we care more if there's a pole in the right hand?
That's why I made this following slide,
Ah,
because I thought the same as well the first 10 times I saw this.
So does this mean we're mapping infinite values to finite values?
Yes, so think about if your f function has more poles than zeros, then every single one of these points is going to map to where on this range space? origin. Okay. So what I've drawn here, you can actually conclude one better. This f function has an equal number of poles and zeros because it doesn't go to 0 and it doesn't go to infinity. Done.
If you have a Nyquist contour and the output of that Nyquist contour encircles the origin, doesn't that mean there's a pole or a 0 in the right-hand plane?
Yes.
Or an equal amount? No.
Well, it means, so if n is non-zero, you're saying? Positive or negative? That means that these have to differ. That's really, I think, all you can conclude. If you don't tell me orientation, if you just tell me number of encirclements, 5,
Okay.
but it could be +5 or -5, then all I know is that these are 5 apart. I don't know which one's bigger.
But you know that there's either poles or zeros in the right-hand.
Yes.
Okay.
Yeah. Either.
Is the usefulness of this just to determine how many poles and zeros a system has?
On its face, on level 1, yes.
Okay.
On level 2, we'll get to how can we make sure that is 0? Or like, how can we design, or how can we read this to tell us how close we are to having unstable poles?
Gotcha.
That's where we're going.
Okay.
Yeah. So let's talk about a feedback control system. This is all review. Everyone is comfortable with this, I think. And so this is what I was getting at the end of Monday's lecture. If I look at the denominator of the closed loop transfer function, the closed loop poles are those s's that make this 0. The s's that make 1 plus k g h equals 0. So one could say that the closed loop poles are the zeros of this function, because they literally make it 0. Now, be really careful with how you say that. I'm trying to slow down to a snail's pace. Closed loop poles, which are relevant to the closed loop transfer function, are the s's that make this function 0, which are the s's, you could say, that are the zeros of this function. That's what the 0 is. Okay? That is going to be our z in our Cauchy's argument principle. Yes, closed loop poles are represented by the letter z. Okay. It annoys me that I have to use that nomenclature, but that is the universally used nomenclature. What are the poles of this function, 1 plus L? Well, they're the same as the poles of this function. If you're a pole of L, you're also a pole of 1 plus L. Because remember, a pole is something that makes a function go to infinity. If you make this go to infinity, you certainly make 1 plus that go to infinity. In fact, it also works the other way around. There is no way that this can go to infinity without this going to infinity, because this is finite. Okay, so from that, we can say that the open loop poles are also the poles of 1 plus L. Okay, so that is going to be our n. Sorry, I had a 50-50. Our p. Okay. Now here is the last leap I'd like you to make. If L encircles the origin n times, what can I say about 1 plus L? I actually think this is the exact reverse. I care about the number of encirclements at the origin of 1 plus L, because that's what my P and my Z relate to. So N, we're going to say the number of counterclockwise encirclements of the origin of the function 1 plus L. If I know 1 plus L encircles the origin n times, I know that L encircles -1 n times.
-1, not 0.
-1 plus 0j, that point on the S-plane, or on the complex plane. Yeah.
I'm confused between Z and G, because if Z is the closed loop poles of this function, aren't they going to be the same poles of 1 plus L of S?
No. So let's take this example perhaps, and we can run with that and you'll see the difference here. If L of S is a repeated open loop pole at -1, so this example could look like doesn't have to, but it could be unity feedback. Then the open loop poles are -1 and -1. But the zeros of 1 plus L are not -1 and -1. The zeros are the ones that make this equal to 0. So that looks like S plus 1 squared plus 1 equals 0. So it's not really important what the roots are. It is important that they're not -1 and -1. Yeah, I mean, this whole class is dealing with the battle between L and 1 plus L, like the mental arithmetic required to see. These things are so similar when you write them, but they are a world apart. But this is saying they're actually not that different. Also, it requires thinking in 4 dimensions, kind of, which is challenging. So, so the point is that this is actually hard in general, especially if this is a variable. But you know what's easier? Finding the open loop poles. That's why we're going to use this n equals p minus z, where we're going to know that, and we're going to know that. We're going to find that, which gives us a number of closed loop poles in the right half plane. And yes, I'm pointing at the letter Z and saying closed loop pole. I mean that. Sorry.
I'm a little bit confused about how are we just going to know the number of encirclements?
The number of encirclements?
Yeah.
We're going to have to draw a Nyquist plot. Yeah, so that's actually the lesson I'm trying to teach here. Is let's draw the Nyquist plot of the closed loop transfer function? No. 1 plus L? No. Just L. Just the open loop transfer function. And if I can count the number of times just L goes around that, I'll have n. So, okay, maybe not a check mark, but a soon-to-be check mark. So here we've got the real part of L and the imaginary part of L. And the understanding now is that I'm not going to draw the domain contour because we're only going to consider Nyquist contours now. Cool.
It's possible to imagine an output contour that has both counterclockwise and clockwise encirclements.
Yes.
Is that something that we'll ever run into, or is that kind of like a mathematical possibility? But
No, I think it legit can happen. So, done. Thanks. So when you get a complicated Nyquist plot, what your best bet is to start at the origin, draw a ray, and count the number of crossings left and right. And once you've taught up those, the net will be your net number of encirclements. Yeah. But I wanted to start easy. Okay, so let's walk through what the Nyquist plot of this example would be. So we know that there are two open loop holes, both at -1. And our Nyquist contour, I think, makes sense to start at the origin and walk up. As I start at omega equals 0, what is the resultant? Cool. 1. Yes, also 1. Right? 1 over 0 plus 1 squared, just 1. So as we walk north on the imaginary axis, does the magnitude of L get bigger or smaller? Smaller. Like, you can feel free to use your Bodhi knowledge of this as well, right? As you increase the frequency, your pole magnitude gets smaller, because it looks like that. Okay. Does the phase, so what, so as I walk north, does the phase of L go positive or negative? Negative, because both poles contribute negative phase, so that's another great way to think about this. We're heading this way and this way as omega increases from 0.
So for that whole part of the Bodhi plot where it's like nothing's happening, that's just your vector staying still.
That's this bit, yeah.
Okay.
Yeah.
So a whole lot of omega, it's right there.
Yeah.
Okay.
Yeah. But wait till we get to omega equals infinity. It's the exact opposite. Anyway, so how about when omega equals 1, what's our phase angle? Each of those gets us -45, but I've got 2, so I'm at -90. So this is the point, omega equals 1.
Would it be a smooth circle?
Not a circle, because it's going to be a spiral-ish, because the magnitude has to get smaller.
Right.
This is probably closer to a circle than I've drawn it, because if you think about the Bodhi plot of this, the magnitude would be close to not changing. But then as we walk further north on the imaginary axis in the domain space, magnitude goes to 0 of L of j omega. What does the phase do? As this gets big, 10 to the 6, this looks like which looks like a negative number. which looks like a west-facing phasor. Okay. So we're going to end up with a spiral like that. Okay. So this point, the origin, rather, is what you get when you plug in infinity j for s. And now we've gotten to positive infinity j, and we start our long journey around the semicircle. What's the magnitude doing as we walk around that semicircle? Constant at 0, because we're infinitely far away from the poles. Then if we emerge from our long journey, start walking north up here, we're going to get the exact mirror of what we have here. So this is omega equals infinity j, also the entirety of this circle, also negative infinity j. And then here, we're getting a traversal as omega increases from negative infinity back to here. So let's put our contour arrows on here. The contour, the Nyquist contour, starts at the origin and goes clockwise, which is why I drew all of our practice contours clockwise. This results in a clockwise traversal as well. Questions on the drawing of the Nyquist plot. This is a proper Nyquist plot. All of the stuff we drew on Monday aren't actually Nyquist plots. They're just graphs of complex functions. This is a Nyquist plot because it arises from a Nyquist contour. Cool. How many encirclements of -1 are there? None. So if we use now, I can fill in the check mark. No right half plane open loop poles, no encirclements of -1, which means how many closed loop poles in the right half plane? None. Yay, it's stable. Wasn't that easy?
Wait, wasn't it like encirclements of the origin and just
Encirclements of the origin for 1 plus L, which turns into encirclements of -1 for just L. And L is generally easier to draw, or, right? It's just a translation left or right, depending which way you're going.
for like three? Okay.
Yeah.
I know I'm not working for this, but would that count as an encirclement of the origin? Since we're hitting the origin.
Agreed that it doesn't actually matter if it encircles the origin. Yes, I think it would. Yeah, you would enclose the origin, or you would touch the origin.
And so is the idea behind this that it's easier to estimate the open loop poles? And so we can already know if those are stable enough?
Yes.
And we're looking.
Exactly right. Right. The step 1 of root locus was plot your open loop poles. So basically all of our analyses start with our open loop poles and the assumption that our open loop poles are easy to find somehow. This is included in that. Okay. Any other questions on this, Ethan?
Did you go over from P to N to Z, like how you got those again? Like just like
For this problem?
Yeah.
Okay, so P are the open loop poles in the Nyquist contour. For us, that was none, because they're both at -1.
Gotcha.
N was the number of encirclements of -1, which for us, the number of encirclements of -1 of L of S, of L of the Nyquist contour. which is this heart-shaped graph. That was also 0. So then the Cauchy principle tells us that z must be 0. And the interpretation is that z is the zeros of 1 plus L, which are better known as the closed loop poles, or the number of closed loop poles in the Nyquist contour, which is the right half plane. Great. You could have done that much easier by solving the quadratic equation that we wrote out right here. Now let me get to the actual point of this. What happens if this is a variable? What happens to this plot? Well, okay, first off, what happens to the p? Stays the same. If I scale this function, I don't change its poles. Does changing the scaling factor up here affect this graph? Yeah, it's going to expand or contract it, depending on if k is bigger than 1 or less than 1. If k is less than 1, I hope you see that it also won't encircle negative 1. Just shrink. But here's the cool part. What if you inflated k? Would it ever encircle negative 1? Could we ever destabilize this by increasing k? It's the same result. Okay. One way to say that is that there is an infinite gain margin in the system. Oh.
When you scale, so does it scale about like the center of that thing, or does it have fixed points at 1 in the origin?
The fixed point is the origin, the only fixed point.
Oh, okay. So the other, it'll scale about the origin.
Right.
Or,
Yeah, you're literally zooming it in or out about the origin. Yeah. Yeah, so the omega equals 0 point won't always be 1. In fact, it'll always be k. The DC gain, omega equals 0. Okay. You good on that? We can't destabilize this by increasing k. If you want to think about it from the root locus perspective, great. If you want to think about that by stretching this out, these little cusps will always be cusps. They'll always miss negative 1. They'll never encircle it, no matter how big we make this heart. If we make the heart bigger, can you imagine a phase margin on this plot? Let's try that out. That's harder to see, but actually probably the most valuable thing here. So let's let k be 4. Perfect. I'm glad I chose the break in the board. That's super convenient. So once I pick a open loop gain, say 4, I've zoomed out or in, I've made bigger the resultant contour. Now, if I were to add a phase delay around this loop, how would that manifest itself in the resultant graph? A rotation. Okay. So if I were to rotate this about the origin, could I get a negative 1 encirclement? For sure. Right about here. Yeah? I hope it won't surprise you that this angle is the phase margin. The phase margin changes with the gain. We actually learned that before. The bigger the gain, the smaller the phase margin, generally. The bigger the gain, the closer these cusps are going to get to negative 1, the smaller the phase margin.
So what is that line you're drawing? Is that the asymptote that it approaches, or is that the line through the point that would hit negative 1 if it approaches?
The latter. So the way that this is usually generalized is a circle of radius 1 is drawn, and then where that circle intersects your Nyquist plot is the point to which you measure your phase margin.
So would that, or could you draw the point where the omega crossing would be, where at which value omega is equal to minus c? Would that be the circle radius 1, right?
You'd have to find, yeah, where the Nyquist plot had magnitude 1, we used to call that omega c, right, in the Bodhi land. Still omega c here, but it's no longer really a crossover. It's the crossing of the Nyquist plot with the radius 1 circle.
Okay.
And then you want to know the phase at that point, and then the phase margin is the difference between that and minus 180. So the definition is the same as one we had last week. It's just graphically different.
So if we rotate this contour towards just touching -1, does that produce like a marginally stable pole?
Exactly right. Exactly right. Right, and so this all comes back to n equals p minus z. P hasn't changed. We still have 2 open loop poles, neither of which are in the Nyquist contour. But if we were to rotate this by an excess of 20 degrees or whatever, then all of a sudden our n goes from 0 to 1, which means that we have 1 right half plane, 0 of 1 plus L, which is a closed loop pole.
So for a gate margin, are those feasible?
Yes, let's change the example slightly, and we'll actually get both finite gain and phase margin. All right. We're still starting with our Cauchy argument principle. P is still 0. N is what we're going to be after right now. So, real part of L, imaginary part of L. When omega equals 0, we're sitting here at 1. When omega equals it actually might not be a bad idea to try to use our Bodhi knowledge on this problem. What's the phase of this at super duper high frequencies? Negative 270. 3 poles, 90, 180, 270. Negative. So we got where it starts. We've got how it ends.
How do you know it ends there?
Because it's more poles than 0, so it has to quote unquote end. And again, it's not an end because it's a contour. It goes around and around. But as omega goes to infinity, which is all the Bodhi plot tells you, as omega goes to infinity, this magnitude, this phase plot goes to minus 270. So all I'm saying is that our phase of L has to come around from 0 degrees to minus 270 degrees. So actually, call it done. Right? We could solve, and I don't have time, but we could solve for this crossing and that crossing. And that would be basically how I draw this more accurately. Just find where this crossing is, find where that crossing is, and then fill in the gaps. But knowing where it starts and knowing how it ends is good enough to make this much of a contour. This is only the positive omega contour. If I want the negative omega, I have to then mirror this. Okay, so there's our Nyquist plot. In fact, it would probably be really helpful to calculate that point, that crossing point. So let's do that now. The real crossing. The real crossing is when L of j omega is strictly real but negative. So that's the real part of this is less than 0. And the imaginary part is equal to 0, which is probably a more helpful way to think about it. Right, this will give us both this point and these points, but it's that point I'm interested in. So maybe I'll sort through the answers at the end. Okay, so L of j omega, if you FOIL it out, you get 1 over 1 minus 3 omega squared plus j omega times 3 minus omega squared. If the imaginary part of this is 0, that means that this has to be 0, even if it's in the denominator. It still works out that way. So I need omega times 3 minus omega squared to be 0. Omega equals 0 is one crossing. I already knew that. And then this will be omega equals the square root of 3, positive or negative. We'll take the, I mean, they're both going to get the same thing. This gives us the omega at this point, but doesn't give us the coordinate of the function. For that, we have to plug it back into L. And that gets us, there we go, negative 1/8. So that is this coordinate. This is 1. This is negative 1/8.
So if your gain is larger than 8, it would
If your gain were, sorry, if the numerator were 8 instead of 1, that would take this yellow thing, inflate it by a factor of 8, which puts this crossing at negative 1, which is our crossover point.
What does that mean? Like changing, because that's your, okay, no, that's exactly not.
It would be like changing your controller gain from 1 to 8.
Yeah.
So then your gain margin here is 8 in decibels. This is 8, which is 2 times 2 times 2, which is 6 plus 6 plus 6 dBs. Pretty nifty, huh? When k is equal to 1, is our phase margin, what's our phase margin?
180.
It's got to be 180, because this only gets smaller. So the only way that we'll get crossing here, if I keep this picture, is if I rotate this entire thing over. Okay. But if I have some gain between, say, 1 and 8, then I'll inflate this enough that the intersection of the unit circle will cross somewhere with an angle less than 180.
If the gain shrunk it, what would the phase margin be?
Then it would be infinite.
Okay.
Yeah. You could lag by an infinite amount, and you would never stabilize. Kobe? Kobe?
No.
Nope.
Well, I was thinking about something like that.
You look like you were thinking about something.
So, yeah, when you tilt it, it's only at 180, or is it like a big margin? Right? Is it only 180 that there's a circle going around?
Yeah, so we're still thinking about circle of radius 1. And so if I were to pick up the yellow thing and rotate it, the only time I would intersect with -1 would be if I rotated by 180. For this gain. If I inflate the gain, then all of a sudden this crossing is at a smaller angle. Yeah.
So the phase margin is 180.
As drawn, the phase margin is 180. Yes. Thanks, everyone.